We all go on vacations, we take photos, we take videos, and we relive our memories. And once in a while, we look at our, say, last year's vacation or one of the memorable vacations from, say, 5 years back, right? But instead of photos or videos, which are good, what if you could not just see them, but actually interactively feel them? What if you could actually go inside the places where you visited once and maybe get a great feel of the environment around, and you could relive those memories in 3D and not just in photos and videos? Well, Nvidia has an answer for all of these. Their latest model is called Lyra 2.0. So welcome to the series on decoding papers with AI, where we take some papers and try to see if we can understand them using AI tools. So today we're going to look into Lyra 2.0 from Nvidia, which I think has been recently accepted in ICLR 2026 and A-Star conference. So this is about how you could take photos, videos, and turn them into a 3D interactive environment. So let's jump right in. So this is a post from Nvidia AI, and it says that today we released Lyra 2.0, a framework for generating persistent, explorable 3D worlds at scale, from Nvidia Research. Generating large-scale complex environments is difficult for AI models. Current models often forget what spaces look like and lose track of movement over time, causing objects to shift, blur, or appear inconsistent. This prevents them from creating the reliable 3D environments required for downstream simulations. Lyra 2.0 solves these by maintaining per frame 3D geometry to retrieve past frames and establish spatial correspondences, using self-augmented training to correct its own temporal drifting. So Lyra turns an image into a 3D world you can walk through, look back, and drop a robot into real-time rendering, simulation, and immersive applications. And this is the visual that they're just showing. It's like, oh my God, is this for real? Or is it a dream, right? Imagine you went to these places and suddenly you can turn these from just photos or videos into real 3D environments. And that's what NVIDIA's Lyra 2.0 allows us to do. Just amazing. I have no words to describe. So here's the project page of Lyra 2.0 from NVIDIA. And as you can see, we saw the same video just a moment back in NVIDIA's LinkedIn. And here are more videos: creating a simulation-ready 3D environment with interactive GUI. So you can see that they not only have those generated videos, they also created a nice GUI which could be used. You could see how we would have seen these types of images in like Google Maps, right? Wherein you would have seen like this is just a, and from here you could see how this entire immersive environment is being built. It's like really amazing, like kind of, it's almost like you're living right there, right in the moment, right? So, and they say, we built an interactive GUI to visualize the accumulated point clouds and enable users to plan camera trajectories, to revisit previously explored regions, and so on, right? And then they also have some scene applications, which also you can hover them to play, and like I'm doing now. So there are a few examples. This is like amazing. Looks like some Buddhist temple or a Chinese temple. Yeah, Buddhist temple is what I'm seeing, or a Chinese temple maybe. And then there's also diverse scene generation, a few more examples, and this is pretty cool. And wow, this is almost like, this is not in, I don't think this is even real, right? So this is like kind of almost a gamified alien-like environment. And let's just go further down, and pretty amazing things. So that further talks about the abstract and then the method and the acknowledgements and so on. So what we're going to do is take this paper. I have also downloaded this paper. So take this paper and like pass them to AI tools and try to see if I can understand what is going on, or maybe get a high level preview of what's actually happening. The first AI tool I'm going to use is SaralAI, which takes in academic papers and converts them into engaging video presentations and slides and other format. The first step is Saralify, and it asks you to just do in with the Google account, and that just will take like maybe a couple of minutes or so. And then it says like once that's done, it asks you if I can configure your own API keys, if I have a Gemini key, or you can also do skip for now, which will just use the system keys that they provide. So the next step is that you could either upload an archive link or a PDF or a LaTeX source file if it's available. My favorite version is the PDF, so I'm just going to upload a PDF. So I've already downloaded this paper, Lyra 2, so I'm just uploading them again. So it's just uploaded this file, and then you can see that it's a 13 megabyte file. So there are a few formats here to consider what we would do. My favorite among them is one-click podcast, which is going to just generate a quick podcast, maybe a 3 to 4 minute podcast, and it's going to tell us like what this paper is all about. And so let's just wait for a couple of minutes and then figure out what happens. So we're here. I generated a video instead of a podcast. So let's see what the video says. It's about close to 3 minutes long about the whole paper. So let's just find out.
Welcome to this presentation on Lyra 2.0, Explorable Generative 3D Worlds. This research was conducted by Tianchang Shen et al. And published in 14th April 2026. Today, we'll explore the key findings and contributions of this important work. Let's begin by understanding the problem this research addresses. Lyra 2.0 is a framework for generating explorable 3D worlds from a single image. It addresses the limitations of current video generation models in maintaining 3D consistency over long camera trajectories, which suffer from spatial forgetting and temporal drifting. The system enables users to iteratively define camera motion to express while relying on the generative prior for appearance synthesis. An anti-drifting strategy is implemented through self-augmented histories during training, exposing the model to its own degraded outputs to learn correction. Lyra 2.0 achieves state-of-the-art performance in long horizon 3D, CONSISTENT video generation and 3D scene reconstruction. Quantitative evaluations show superior results across metrics like SSIM, LPIPS, FID, subjective quality, style consistency, camera controllability, and reprojection error compared to existing methods. Qualitative results demonstrate the ability of Lyra 2.0 to maintain realistic structures and appearances over significantly longer generation horizons than baseline models. Lyra 2.0 successfully enables the creation of large-scale, explorable 3D environments by addressing long horizon consistency challenges in video generation and improved 3D reconstruction robustness. The framework is suitable for interactive exploration, VR, and simulation. Limitations include the focus on static environments and potential reproduction of photometric inconsistencies from the training data, which can affect reconstruction quality. Lyra 2.0 presents a significant advancement in generative 3D scene creation, enabling the generation of explorable, persistent 3D worlds from single images. By effectively tackling spatial forgetting and temporal drifting in video generation and integrating with a robust 3D reconstruction pipeline, the framework provides high-quality, scalable 3D assets for various downstream applications, including embodied AI.
That's really cool. So my understanding is the following. So you can take an image, and from that image, you can kind of explore a 3D world by you start with a camera, like a camera pose, and which is going to be like a set of like orientation and scale in different directions. And what you would do is that for each frame, you would define like from time to time what the camera trajectory is going to be. And this is usually done in lots of VR applications, like you can do it in also like Unity like environments, wherein from an image you give like a 3D trajectory, camera trajectory, and you could see that it's going to the video. Once you click on generate, it will follow that particular trajectory from the initial starting point. So I think that is one of the things that this mainly does. And of course, like what usually happens is that there's going to be a lot of shaking, drifting when this happens. And then there's also going to be a lot of like a spatial forgetting. Sometimes you may forget, like if you've seen some game environments, usually they don't forget, they are pre-programmed or all of this really nicely. So I think this paper also probably tries to solve these two main problems and then does that. So this was a quick like 3-minute introduction. So let's maybe go in deeper and see what this paper is trying to tell us. The next format we're going to use is poster. So given a paper, Saral quickly generated a one-click poster. So this has the paper title, the authors, and so on. So let me just try to go one step by step. I mean, this is the full poster. It's really done, almost like the ones we print in conferences. So it says, let's start with the abstract. Scalable generative 3D reconstruction to large environments requires maintaining consistency over long trajectories, a task hindered by spatial forgetting and temporal drifting in current video models. Lyra 2.0 addresses these challenges by decoupling geometric tracking from pixel synthesis. Okay, now I see some more information. Through a 3D cache and utilizing a self-augmentation training scheme to mitigate error accumulation. This framework enables generation of persistent long horizon video trajectories that can be reliably reconstructed into high fidelity 3D Gaussians and surface meshes. Experimental results, so it's really good. So basically, like from what I'm understanding, is that you have 3D generation synthesis, pixel synthesis in one form, like where pixels and videos or voxels are generated. And then you also have geometric tracking where you want to track the different poses from the cameras, right? And this paper basically tries to decouple them. And then it also uses a self-augmentation training scheme. So let's further see what more this is. So generation, in the introduction is, generative reconstruction models fail to maintain global consistency in large environments, and autoregressive video generation is susceptible to error accumulation, leading to temporal drifting and structural distortions. We've seen this many times. I myself have seen. Lyra as proposed, 2.0 is proposed to enable the creation of an expansive, explorable 3D worlds by integrating long-range geometric memory with a robust generative pixel prior. Okay, interesting. The framework maintains an incremental 3D cache of per-frame geometry to retrieve relevant historical context and establish dense correspondences for target viewpoints via canonical coordinate warping. A self-augmentation training strategy exposes the model to its own denoise predictions. The resulting long horizon videos lifted into 3D using a feed-forward 3D Gaussian splatting pipeline fine-tune on generated data to ensure robustness against minor multi-view inconsistencies. So here's one of the figures that was there in the paper. And so it says that really good, achieves like really good methods over the benchmarks and lots of metrics like FID, SSIM. So the conclusion is that Lyra bridges the gap between video generation and large-scale 3D reconstruction by effectively managing long-range, spatial, and temporal dependencies. The generated high-fidelity 3D assets are simulation-ready and have been integrated into physical engines like Nvidia IceXM for embodied AI research. Like that's one of the frameworks that's used for robotics from Nvidia. So further work will focus on expanding the framework to support dynamic environments. So that's nice. And here's a paper. So this is a camera trajectory is what is shown. So usually there are like absolute poses and relative poses, and pretty sure these things are going to come inside. And then there's point cloud and then 3D like Gaussian splats. Those are also probably going to come. So it's probably very interesting. So this at least shows a very high level overview of what it is. So we'll explore a few more formats and see what more we can understand from this paper. So now I'm come to NotebookLM. This has generated an amazing video about this paper, Lyra 2.0. It's a 7.5-minute video, so let's see what it says.
With a single static photograph. The goal of generative reconstruction is to use this initial 2D image as the seed to generate an entire explorable universe. To do this, engineers use camera-conditioned video diffusion models. These networks synthesize dense, novel views, which are then used to extract explicit 3D geometry. But scaling this process from a single room to massive, complex environments requires the generation of thousands of frames along a continuous.
So what is really nice is that we saw what Nvidia's on the website and from their video, they were trying to generate this 3D world. And but what we sent showed as input to NotebookLM is actually only the paper, so which probably will not have the 3D world, right? So what it's actually done is that it's basically absorbed that concept and it's right away this is generating 3D worlds, and it's also like put out those trajectories, camera trajectories, like these green color lines. I mean, of course, illustrations of camera trajectories to illustrate how this is being done. So that is pretty impressive.
Winding trajectory. Here, we hit a severe engineering bottleneck. Modern latent video models, built on diffusion transformers, generate frames autoregressively. They are constrained by a strictly finite temporal context window. To achieve unbounded scene exploration, an AI must navigate infinite spatial dimensions using a tightly restricted memory. Think of a fixed temporal context window as a sliding memory limit moving across a sequence of generated frames. This creates the first major failure mode, spatial forgetting. As the camera moves forward, previously generated regions inevitably fall behind the trailing edge of this window. When the camera path loops back to these forgotten areas, the model has no reference to what it built. It is forced to hallucinate structures from scratch, breaking the
So this is amazing. It's trying to say that when it comes back, what we call loop closure in SLAM and other areas, what happens is that since this autoregressive model only have a very temporary small context window, it doesn't remember what it generated first. So when it comes back to the original place, it starts hallucinating and then it gives completely different environment. And this is what we do not want, and that will not happen in a real life or even in a game. So that's what this paper is probably trying to address, and really nice illustration here.
global layout completely. The second failure mode, temporal drifting, is an inherent flaw in the autoregressive generation process itself. Autoregressive models compound errors step by step. Over time, small synthesis artifacts accumulate, distorting textures and geometry in a continuous feedback loop until the scene appearance decays. Lyra 2.0 is a generative reconstruction framework engineered.
So here what they say is that the videos, like usually it starts generating really nice initially, but as it continues, there's something called like temporal drifting, and starts distorting what we get as output. And that's another well-known problem. So that's what it's trying to illustrate and how this paper is trying to fix.
Specifically to bypass these twin degradations without sacrificing output fidelity. Achieving true 3D consistency requires overriding the diffusion model's natural tendency to forget its past and corrupt its own future. Earlier attempts to solve spatial forgetting maintained a single, global 3D point cloud accumulated over time. The problem is that generative artifacts degrade this geometry, and the model then conditions future frames on those very errors. Lyra 2.0 completely decouples geometric tracking from pixel synthesis. Instead of a global map, the system maintains strictly independent per-frame point clouds.
So my understanding here is that so they maintain a large point cloud of, say, of a city or other things. So there are usually these geometric errors that start, it's called like error propagation, accumulating. So by geometric, it's like you start a camera at a point, at an initial point, and then you kind of track the camera for a certain number of, say, trajectories. What happens is that error starts accumulating then. And as it goes further and further, the error just keeps accumulating. This is called the one of the error, like, and starts propagating as well. So, and what they mean by geometric is that it just uses like classical computer vision methods to kind of estimate the geometry, the absolute poses and the relative poses, which are like the scales and orientations and so on. So that's what, and what this paper tries to do is that it tries to decouple the trajectory and the pixels, the videos that are generated is what it's trying to claim.
These isolated geometries are never fused together. By keeping them separate, the system prevents cross-view misalignment caused by imperfect depth estimates from accumulating. During an autoregressive generation step, Lyra 2.0 uses a geometry-aware retrieval mechanism. The target camera view projects all of these past point clouds onto its own 2D image plane. The system calculates a visibility score by computing the minimum projected depth to handle occlusion. This mathematical routing identifies the specific history frames with the highest spatial overlap to the target view. Because this relies entirely on 3D spatial geometry rather than the temporal sequence, it perfectly recalls aligned observations, even if that region was generated hundreds of frames ago. This chart shows target view coverage against the number of retrieved frames. We can see that pulling just 5 spatially relevant frames yields optimal target coverage while remaining computationally efficient. Long-term persistence is achieved by treating 3D geometry strictly as a search index to retrieve past context, not as a rendering canvas. Once those 5 relevant frames are retrieved, we hit another architectural challenge. How do we establish dense spatial correspondence inside the diffusion model without re-injecting past rendering errors? Standard depth-based warping fails here. Warping RGB pixels inherently creates stretching and disocclusion holes, which the diffusion model then lazily adopts and reproduces as ground truth. Lyra 2.0 replaces the RGB image entirely with a 3-channel canonical coordinate map. This map carries 0 photographic texture, representing only normalized X, Y, and Z spatial positions. This pure coordinate map is forward warped using full resolution depth, bending perfectly to the depth contours to establish dense geometric tracking. These warped coordinate embeddings are injected directly into the transformer's self-attention blocks. This provides perfect spatial grounding, while forcing the model to rely entirely on its learned generative prior to synthesize the visual appearance. By stripping away flawed photographic data and feeding the network pure geometric logic, the system resolves multi-view inconsistency autonomously. Recalling precise spatial data solves forgetting, but we still need to arrest temporal drifting. A perfect spatial map is useless if the temporal sequence itself decays.
This is really cool. I myself maybe need to understand this further. So usually there are like these grids, and you do like as the scale changes, you do a uniform warping, and then the whole grid is warped in the same way, a 3D grid. And I think from what it tries to say here is that this does not do a uniform warping, but it tries to maybe do some kind of a localized warping, which they call this as a canonical coordinate frame. Like I said, I have to look into it a little bit more, and that is probably fed into AI, which tries to mimic the realistic scenes in most cases.
To stop this, Lyra uses a context compression strategy called FramePack. Recent history frames are processed as fine-grained tokens, while distant frames are heavily compressed into broad contextual blocks. Crucially, the very first generated frame, the initial input image, is always kept uncompressed in the context window. This acts as a permanent anchor point to prevent global color and texture shifts. But as the camera explores new areas, these early anchor frames move entirely out of view. Compression alone cannot suppress drift in newly synthesized, unseen regions. The final intervention is a self-augmentation training scheme. Instead of training the network on perfect ground truth frames, Lyra 2.0 stochastically conditions the model on its own one-step denoised predictions. By exposing the model to the exact error distributions it will encounter during generation, the network learns to actively suppress drift rather than propagate it. These distinct anti-forgetting and anti-drifting mechanisms converge into an interactive exploration interface.
This is pretty amazing. Again, I have to a little bit look into this more in detail. But from what it's explaining, it's like, I think it's like it tries to, instead of suppressing the errors, it tries to even have those errors in the system and tries to like maybe say that it's like the positive and negative kind of a thing, and that helps in like further suppressing it, so on. I'm not sure if that's what it's trying to say, but if that is, then that's really nice.
Define long horizon camera trajectories. This triggers the retrieve, generate, and update loop, allowing the model to endlessly expand the initial seed image into a continuous environment. There is one final operational hurdle. Even with these controls, generated video sequences harbor minor multi-view inconsistencies that easily break traditional 3D reconstruction pipelines. To lift the 2D video into a robust environment, the generated sequence is passed to depth anything v3, a feed-forward 3D Gaussian splatting foundation model. Because this reconstruction model is fine-tuned directly on generative data, its multi-view prior is conditioned to ignore minor visual artifacts, outputting clean and coherent 3D structure. The resulting spatial geometries achieve scale, transforming a single input view into expansive, explorable maps. These generations maintain strict structural coherence across the entire camera trajectory, completely eliminating hallucinated layout breaks. Finally, these Gaussian environments can be extracted into hierarchical sparse grid surface meshes, ready for direct deployment in embodied AI platforms like Nvidia Isaac Sim.
Wow.
Lyra 2.0 proves that to build infinite, persistent worlds from a single photograph, an AI architecture must abandon rendering the past and instead learn to mathematically route it.
Wow, just amazing. It's like I want to just keep listening to this, watching this again and again, then even reading the paper. I mean, just look at the how it's actually been able to like put this concept from the paper to an amazing cinematic video. I think this time I chose a cinematic video. That's why you have these amazing illustrations. Let me just listen to it for maybe the next 15, 20 seconds. Even the introduction it gave was pretty amazing.
We begin with a single static photograph. The goal of generative reconstruction is to use this initial 2D image as the seed to generate an entire explorable universe. To do this, engineers use camera-conditioned video diffusion models. These networks synthesize dense, novel views, which are then used to extract explicit 3D geometry. But
this is too good, right? I mean, you just want to keep watching it again and again. It's so addictive. That's a good word. So that was so pretty awesome. So the last format I have is again from NotebookLM. This is going to be a slideshow. It's generated slides, which can be downloaded both in PowerPoint and PDF. You could possibly see lots of similarities with the cinematic overview, but this is like if you don't want to watch a movie but just want to get this information just by looking at slides. Let's see what it says. So Lyra 2.0, the blueprint for infinite 3D worlds. Single image to a Gaussian splat to an interactive simulation. So it's also done like you can see a single image here, and then you could see how this is, you have this trajectory mapped here, and then you also have like an illustration to show how you have two parts of the image, it's almost like a 3D world now from this image, right? The generative reconstruction bottleneck. The promise is that feed-forward 3D reconstruction from video models allows for rapid creation of environments without real-world capture. So you can quickly capture like a 3D from video models. But the reality is that scaling this to large environments demands autoregressive generation over hundreds of sequential frames. So you have to they showed the context window problem, you have to have generation which are consistent over hundreds of frames, right? The breaking point is that current video diffusion models inevitably fail at long horizons due to finite temporal context, like what we see here, and catastrophic error accumulation. This is the error accumulation I was talking about from geometric properties like force estimations and so on. So they've also illustrated this in the top side. You have frame 1, frame 0, frame 10. When it comes to frame 50 to 100, you can see that there are some drifts and distortions. And when it comes to 200, it's catastrophically failed. It's just going to generate some gibberish or something. Degradation diagnostic tables. So you have visual system root cause, spatial errors, and temporal errors. So it's divided this into nicely four, a 2x2 matrix. So here's the symptom for spatial errors. Hallucinated structures and layout collapse upon revisiting previously explored areas. So what happens is that when there's loop closuring, you're going to come back to the same point. Hallucination starts, right? And finite temporal context window. Early observations, so what is the root cause for this, right? Early observations are purged from memory, so breaking global layout consistency. So that's why this happens. Then what about the temporal errors? Severe color shifts, structural distortion, and melting geometry over time. So you see these effects, blurring / melting effects. And this is because of the autoregressive error accumulation. Like small synthesis artifacts at each steps compound in a feedback loop. So as you saw in the previous slide, how we there are some distortions here in between frame 50 to 100, but by the time you get to 200, it's already accumulated quite a lot of error. The evolution of spatial memory. It says why tightly coupling geometry with appearance synthesis is a flawed paradigm. So by geometry is like usually in computer vision we refer to geometry by the camera pose, the camera estimation, and then the depth and all of that. That is usually referred to as the geometry. And a scene usually is described by both the camera and pixels, like the camera coordinates, the position, the pose, as well as the pixels that are there. And I think this is trying to say that this is the problem with the current synthesis paradigm. So it says again, the temporal problems are context window length. Okay, so it's just context window length. If it's purely temporal, it's okay, but global 3D accumulation and decoupled routing. Okay, so these are some of the previous methods that have been proposed, and it says how Lyra 2.0 is trying to have green for all of these, right? So the previous method, I think 1.5, that did not have a context window, but global 3D Gen 3C had this. And this one, resiliency to depth errors, both of these were not resilient to depth errors. Long range consistency, this was not, but this was partially there. It degrades over time. Camera controllability, Gen 3C was able to control, but not this one. Whereas Lyra 2.0, it kind of ticks all the boxes here. Strict view control without rigid pixel constraints. Lyra 2.0, autoregressive flywheel. Okay, and this is, I think somewhere it says there was a 3-step, right? The first step is retrieve the spatial memory. Query the 3D cache to find history frames with maximal visibility of the current target viewpoint. So I think it stores some frames and it tries to kind of have a query retrieval format. Generate a DIT context. Condition the WAN 2.1 14 billion model on both temporal history, frame pack, and dense 3D correspondences of the retrieved spatial frames. So this is the geometry, the poses I was mentioning about. So what it does is that there is temporal history from frame pack, which has all the times information. There is dense 3D correspondences from the retrieved spatial frame. These two then sent into a WAN DIT 2.1 14 billion model, and then you get an output. This output probably is a synthesized output. And then there is also this 3D cache, which is kind of also feeds in here, extracts the full resolution, depth, and camera parameters into the newly generated frame and append it to the per frame point cloud memory. So basically, there is the point cloud, an extracted point cloud. Probably this is the one that is. And then this one updates it with the depth and the camera parameters and appends it to the per frame point cloud memory. So I think that's what is happening here. So you have the camera parameters, full resolution, depth, and the per frame point cloud memory, and then it kind of into here. I think, yeah, again, I don't completely understand each and everything, but at least at a high level, I think this loop is what is happening. The 3D cache. Isolation over accumulation. The trap of global fusion. Fusion generated frames into a single global point cloud guarantees that cross-view misalignments from imperfect depth estimation or compounding to corrupted reconstructions. So this is the Lyra solution. Maintain a per frame 3D cache. Geometry is stored independently to avoid compounding errors across over time. So that's an interesting part. So instead of accumulating all the information for every frame, you have a new 3D cache, is what I think they're trying to show. Visibility scoring. To retrieve memory, the system projects history frames onto the target image plane and selects up to 5 frames that maximize novel spatial coverage. This is something interesting which I've maybe not seen it before, but they're also trying to see which one gives a good quality image that is generated. Yeah, this is the very interesting one. This is what I was, I think, trying to tell before. From my understanding, you have a grid. Usually, the grid is you have some warping here, warping there, but this was I think the canonical warping is what they talked about. It's very interesting. goes back to like computer graphics, computer 3D, I mean, like computer vision, like very the basics. So it's just the problem with RGB warping. Forward warping RGB creates disocclusion holes with stretching artifacts, which the model basically copies. So that's where it tries to, the copies, and then it accumulates over time. Equation 3, visualize. Lyra assigns a canonical coordinate map, CJ of UV, to retrieve history frames. Routing, not rendering. By warping coordinates instead of pixels, the video model knows the exact geometric correspondence, but must use the generative prior to synthesize the actual appearance. So it's like it knows what it's trying to say maybe is that it knows the geometric correspondence where it should go, basically from the previous prior frame, but kind of it uses its generative prior also, like what is generated, to synthesize the actual appearance. So the decoupling principle, one more example illustration to show here. Geometry for routing, generative AI for appearance. So it's basically trying to emphasize this point again. Uses explicit 3D proxies only to retrieve relevant history and establish spatial correspondence. Imperfect depth is tolerated, but it's only a map. So this is only for like routing, and then even if there are some errors in the depth, it's still tolerated because it's just a map. And then generative AI for appearance. The WAN 2.1 DIT resolves inconsistencies, fills occlusion, and hallucinates missing details using its vast learned pixel prior immune to like rendering artifacts. So tight decoupling. So you can see that this is like more like a map synthesis, like map, like a routing trajectory, whereas this is like a actual image that is generated. And these two are decoupled. I think that's what they're trying to say. Tight decoupling. Tighter decoupling generated pixels to noisy 3D geometry causes catastrophic error loops. Lyra breaks the cycle by decoupling them. And the root cause for drifting is observation bias. So there's the root cause of drifting. Why does it start drifting? So in the training state, what happens is that you have these camera pose, and then you have these more image pose, and so on. In the inference, what happens is that you have camera, and then it just starts getting more blurry, and so on. Context is not a cure. While techniques like frameback successfully compresses history, they don't fix the underlying train test discrepancy. So this is like an illustration of frameback. So during training, the DIT conditions on perfect ground-truth frames. At inference, it must condition on its own flawed outputs. Without seeing flaws during training, the model cannot correct them. So that's the other thing it's just showing here. The drift vaccine. So this is the other method that the paper is proposing, called self-augmentation. So let me try to understand this. There is a pristine ground truth image, and then there is a context window. It's going to have a few context window. Then artificial noise filter with 70% probability, which goes into a one-step DIT denoising, and you get a slightly flawed deconstruction. So this is like a classical diffusion, like a pipeline where you have this, in the training, you have this noise and diffuse predicted image kind of a thing. Simulation failure. During training, Lyra intentionally corrupts the history latent using a flow matching schedule. Forced correction. The model performs a one-step denoising pass, teaching the DIT to denoise toward a clean target despite receiving corrupted context. Built-in immunity. So in this way, like it tries to give me, I think this is where the video was trying to say that maybe it did not illustrate it this way, that it tries to, like, instead of suppressing the errors, it tries to model the errors, or have the errors in the system so that it learns from the errors. The model actively learns the drifting artifacts during autoregressive inference with minimal computational overhead. An unprecedented long horizon consistency. It shows how Lyra is able to get amazing results. I mean, looking at this, I may not be surprised if Lyra 2.0 is going to be one of the, I think, either one of the best paper awards contenders in ICLR, looking that it's giving such good results. So I'll be checking back to this video when the results come in. So Lyra achieves top scores, and these are the usual quality metrics: SSIM, structural similarity index, FID, Fauchelet inception distance. This one maybe I have to check, I'm not fully sure, and a few more quality and consistency metrics. Lifting to 3D feed-forward Gaussian splatting. So it says fine-tuned foundation, utilizing depth anything V3, fine-tuned on generative scenes to tolerate minor inconsistencies, optimized density, a modified Gaussian DPT head reduces the Gaussian count by 4 times, making high-resolution outputs viable for real-time rendering. Hierarchical sparse grids allocates fine cells near generation viewpoints and core cells in the background, extracting massive seamless surface meshes. Okay, maybe this is a little bit over, like right now, having already gone so technical, I'm kind of getting a little heavy here. So it says real-time world building. So this is an input point cloud and trajectory, and this is the camera path of the trajectory, and then you have the point cloud, and then you have a very high resolution output. It's really amazing with 13 times acceleration. So you have a DMD distillation. Lyra 2.0 student model generates frames in 4 denoising steps, and then a single pass inference, and then a result is an interactive 3D GUI where users can define arbitrary camera trajectories and iteratively expand on the fly. That's just really nice. Many of these software nowadays, rendering software, you can just draw a trajectory and ask it to, like, in a 3D environment, and ask it to, like, just render, so you'll get that rendering thing. So that's what this is referring to. The explorable asset ready for simulation. So is that you have 2D input, the sparse grid mesh, and then you have a 3D world. By decoupling routing from synthesis and vaccinating the model against drift, Lyra 2.0 bypasses the traditional limits of generative reconstruction. High fidelity 3D Gaussians and surface meshes can be directly imported into physics engines like Nvidia ISXM, enabling scalable, physically grounded robot training without real world data acquisition. So that is amazing, because Nvidia has this amazing framework for robotic experiments called the i6sim, wherein you could just define these 2 robots. So, but previously, I think you had to go and physically get all of these and then tune it yourselves. This would probably try to reduce that, eliminate that, if you could do all of this just from a single picture, and so on. So that's it. That's the last slide. And definitely the slide was really, really good. And it was not just the same as the cinematic overview. So it did give a lot of information that at least I found otherwise. So this, again, one of the main objectives of this Decode papers with AI is that you have these massive papers, and they're going to have a lot of depth and technical depth. So you're just trying to use AI tools to try and see what we can understand from this paper. Of course, this is not the same as reading the paper and trying to understand all whatever is inside. This is more like a quick preview of what probably is inside, and we could be wrong, and it depends on like so many other things. But again, I feel that mostly these AI tools are giving some kind of a high level overview of what's there in the papers, and we could probably go and like look into these papers a little bit more in detail. I think this is like definitely helpful to kind of before reading the paper, this is a great exercise, and then reading the paper would be even better, because we may have already seen some of this before. So just going over the paper is like a really long paper, but at least like it's good to see that some of these things, whatever we saw, we already saw in different formats. So it's nice to see it that way. So I think that's the end of today's video. So until next time, we'll come up with another paper. So that's it.